Okay, so kind of to wrap up our Appendix 1, A1, the third day we're looking at it here, just a few more things with rational exponents and radicals. So hopefully by now you're good at converting from one to the other, rationalizing things like that. Okay, so here we have this simplified problem. I think it was in the book. I just thought it looked interesting, so we should try it. There's just a lot going on there. So probably the first thing that hopefully you notice is within the radical, there's an x to the sixth over an x cubed. So you can simplify that, right? So you subtract them, you get x to the third, and it would go up top. So we have the fifth root of 4x cubed y over 9. That seem reasonable so far? Now at this point, there's nothing else that's going to simplify inside. And actually, we're in a case where we have a denominator that we need to rationalize. Right? We have a fifth root of 9 on bottom. And here's a case where if we just notice something about the number 9, it'll make it much easier for us and actually help us to get this correct. Is that 9 is the same as 3 squared, correct? So when we go to rationalize, I'm going to choose to rewrite this as the fifth root of 4x cubed y over the fifth root of 3 squared. Okay. Because as we talked about before with rationalizing denominators, right, we're going to try to get a fifth root of 3 to the fifth power. Right? There's a big advantage because if you use 9 and you try to get 9 to the fifth power, then you're multiplying by really big numbers that we probably not be able to do by hand. This we should be able to. So here we get the fifth root of 4x cubed over x cubed y, the fifth root of 3 squared, and here, because we want 3 to the fifth underneath that fifth root, we're going to multiply the numerator and denominator by the fifth root of 3 cubed, right, because 3 plus 2 is 5, over the fifth root of 3 cubed. Again, we needed this down here. The part in the numerator is just there because you have to deal with the numerator too. It's just part of the deal, just part of what's going on there. So doing this now, we probably want to put this together since this is going to become the number 27, right? 3 times 3 times 3, and then we'll probably want to multiply that by 4. And that's about as much mental math, like paper and pencil. That's, 27 times 4. It's 108. Let's see, we have 4x cubed y times 27, and then over the fifth root of 3 to the fifth, right? So we needed 3 to the fifth, so we left them all as powers of 3. Here we have to simplify, so we'll actually turn it into 27. That's what we're doing there. So now the numerator, you get 4 times 27. Worst case, you work it out, right? However you do, 27 times 4. You get h, carry the 2, you get 108. Or you do something different. You do, you could do 4 times 20 plus 7. You guys ever do that when you have to do things by hand? You could do a little distributive property. So then you get 80 plus 28, which is 108. Just some different options there. So up top, we'll have the fifth root of 108 x cubed y. Then on bottom, which is what we needed to do, we have the fifth root of 3 to the fifth. The root and the radical, or the root and the power cancel, so that'll be over 3. So there we'll get the fifth root of 108 x cubed y over 3. All right, so last little thing we want to talk about here are at times, if you've noticed anything the last few days, there's never been addition or subtraction in any one of these problems, right? All those exponent rules we looked at, they all were multiplication, division. You might add the exponents, but the terms themselves, it doesn't happen because it's really hard to get those to work. So we have a couple that will here, but so what we're looking for is like terms. And this is like back when you're in Algebra 1, you know that like 3x you know, that if you have 3x plus 2x squared, you all know that we can't add those together, correct? Because they're unlike terms. Even though they have the same variable, they have different powers. It doesn't work. Okay? Well, radicals kind of behave the same way. So if I have, you know, 2 square roots of 5, and then I have 3 more square roots of 5, guess what we end up with? 5 square roots of 5. The same thing. These behave just like the x's would behave. They look different. They look strange, right? But it would be 5 square root of 5. Because you just did 2 plus 3. You had 2, you got 3 more, you got 5 total. The thing themselves doesn't change, right? So if you get 2x plus 3x, you just get 5x. Stay the same. So if we now that'll lead us to a question like number 3 or number 2 here, this example. If we look at it, are these like terms?
No.
Now I'm pretty certain 175 and 28 are different numbers. Okay? I don't know much, but I'm pretty good with that one. Well, what happens here is sometimes with this, if you look, 175 is not a simplified radical. There's a perfect square that goes into 175. Hopefully you guys know it's 25, right? It's like a $1.75 is like 7 quarters or something, or anyways. And then 28, there's a perfect square that goes into 28. That's 4, right? So again, we want to rewrite this then as 2 times the square root of 25 times the square root of 7 minus 4 times the square root of 4 times the square root of 7. So I took each of these numbers and broke those into factors. Now, because it's a square root, we're only looking for factors that are perfect squares, right? So our perfect squares, that's your list of, well, 1 doesn't help at all with this, but you could have 4, 9, 16, 25, 36, 49, 64, etc., right? 2 times 2, 3 times 3, 4 times 4. So that's what we're looking for there. Because now, I mean, I don't think you need to probably see this step, but this is like 2 times the square root of 5 squared times the square root of 7. And then 4 times the square root of 2 squared times the square root of 7. Just simplifying here. So 2 times 5 times the square root of 7. 4 times 2 times the square root of 7. Get rid of these perfect squares here. And then from here, we can all do 2 times 5, right? It's just 10 radical 7 minus 8 radical 7. Well, you have 10 of something, you get rid of 8 of them, you got 2 of them. So 2 radical 7. Okay, so example 3 here, we have a couple radicals added together. Again, as we just talked about with like terms, we can't really do anything unless the radical parts match exactly. So what we can do here is we're going to simplify these, and we have the square root of 18. I know that that's 9 times 2. So we can say, so the square root of 9 times the square root of 2, the square root of x squared, times the square root of x, or y. You don't need to write that much out, but I think it's the most obvious way of kind of what we're doing there. And then we put the plus sign. Now, addition and subtraction are big things, and then it's going to separate. We have 2 terms here, right? These are factors of this term, but then when you get the plus or the minus, that's a significant thing that we'll pay a lot of attention to moving forward. And then here we'll get the square root of 2, square root of y squared, square root of y. Again, I'm looking for things that are squared, because when they're squared, or they're a perfect square like 9, I can take the square root of them. So here, in this first one, we have 3 times radical 2 times x times radical y. And then radical 2 times y times radical y. So now again, we'll clean it up. We'll put everything that's not under the radical to the left. Everything that is will still be under the radical. So we have 3x radical 2y plus y radical 2y. Now at this point, we don't have like terms. The radicals match, which is great. But this has a y and this has an x. So the variables don't match, even though the radicals do. This would be fine really to stop here, but you will see this in the future, so it's good to look at. Is we do though, if we look at these two terms, we do have a common factor, correct? They both have a square root of 2y. So a lot of times you'll see this written as you'll pull out the square root of 2y and you'll be left with 3x plus y. Nothing I'm going to expect you, just something I wanted to show you, right? It's not going to be on the quiz tomorrow or anything, but you should definitely be able to get to this line, right? We could all get to here. This step is sometimes useful, sometimes not useful. A big part of studying algebra and pre-calc is to figure out which form is going to work best for you. Okay, so definitely make sure you can get to here. The next one's just kind of some bonus information there. All right, and lastly here, this fourth example, I just thought they were neat problems. They remind me of old teaching ACT or SAT prep classes where they give you two values and you have to compare them. And they get a little trickier. But so here, it really just what we'll have to do is, like this is the number 2. I can compare 2 to anything. That's pretty good. Now 2 to the negative third to the 1/3 power, I'm going to need to investigate that to see what that is. That looks a little bit weird, right? So let's figure that out. So here, you have a base to a power raised to another power. So what do we do with those exponents there? Multiply. And that would give us 2 to the negative 1 power. Okay. How do we get rid of a negative exponent? Flip the base, move it to the denominator. So we get 1/2 compared to 2. I mean, Pac-Man eats the bigger number. Or alligators or whatever you use, right? It'll be the less than symbol. So we'd say 2 to the negative third raised to the 1/3 is less than 2. When I was a little kid, Pac-Man was popular, so Pac-Man was the thing. Probably alligators. All right, so we got another one here. If you want to try that, go ahead and take a second. Okay, this last one looks, again, a little tougher, I think, but let's try it. So we have 4 to the negative 2/3. I'm going to go ahead and work up here up on the board because that looks like it's a little more involved. So the first thing I'm going to do is write it as 1/4 to the 2/3 power because, I mean, why not, right? And then here we get 1 over, well, let's see. Couple things going on here. Now, we're going to square it and we're going to cube root it, correct? So if we write the cube root of 4 squared, it doesn't really simplify very nicely, does it? Okay. But do we realize that 4 is actually 2 squared? Like, which you could get something to come out of that. So you could write it here as 1 over the cube root of 2 squared squared, which would be 2 to the 4th. Right? 16 is 2 times 2 times 2 times 2, or it's 4 times 4. And then here, I could take out, let's see, 1 over the cube root of 2 cubed times the cube root of 2. And again, this is a little challenging, right? That's why we're practicing here. So we get 1 over 2 times the cube root of 2. I realize it's not rationalized. I really don't care because we're just going to put a less than, a greater than, or an equal. It didn't ask us to rationalize it. We're just trying to compare these numbers. It's still going to be hard to compare because that's a weird number. Well, let's see. 3 to the negative 3/4. That's 1 over 3 to the 3/4. Yes?
So, wait, why?
So here, for this one, we have 1 over the 4th root of 3 cubed. This is pretty awful. I'm interested. It's an interesting problem. I'm trying to figure out how to do it. Because, I mean, obviously, if you have a calculator, you just type it in and you put the symbol. That's not where's the fun in that? That's just the 4th root of 27. That's weird. So here we're comparing, okay, so now at this point, we have all this work, right? I think that what's probably going to be easiest is here, this last step, I'm not convinced that that's really that useful. I'm thinking if we could see the cube root of 16, you could compare that to the fourth root of 27, and we could get a decent idea of what's what. It's kind of my thinking. So let's see. 1 over the cube root of 16. Well, what do we know about the cube root of 16? What's between the cube root of, let's see, what are our perfect cubes? We have 2 cubed is 8.
27.
And 27. So it's somewhere between 2 and 3, right? So this is this number. Let's see, the cube root of 16 is less than 3, but it's bigger than 2, right? And then we have the fourth root of 27. So what are our perfect fourth powers? Well, 2 to the fourth is 16. 2 times 2 times 2 times 2. And then 3 times 3 times 3 is 81. So that's also between, this is not going very well, is it? No. Anybody have a better solution for me?
Calculator.
Calculator doesn't seem very sporting, but yeah, I'm starting to think that maybe that's the way to go here. Oh, well, maybe we should try something different. Yeah? Let's try. You guys go away there. We don't need that. Sometimes, I usually don't erase stuff, but this time I went ahead and erased it. So this one, let's look. This would be, if I just, it would be 2 squared to the negative 2/3, correct? So we get 2 to the negative 4/3. And this would be 3 to the negative 3/4. I'm really not digging this at all. We got that whole between thing. I wasn't really liking that. Well, I think we're just going to have to come back, and I'll leave this to the viewer to kind of work out a good solution for this. I'm not going to expect you to do something like that. I just thought it would be fun to try.
So this is what the ACT look like?
There are some weird stuff. Oh, I did go and look at this problem. I actually looked the solution up. If you're on watching the video, I don't think you can do it by hand. They just typed it in the calculator and did it. So I just picked one that was way too hard for us to do. But I think it's important. You can kind of see the struggle, and sometimes things are difficult, and you might learn something, you might not. So there you go.